Okay, so today today is going to be our last lecture. We will not have a lecture on Wednesday, and we're going to look at deep reinforcement learning, which is a little different from the things that we've seen so far. This is the area where reinforcement learning was traditionally developed in robotics communities. You know, you have robots, you want to take actions, and I'll just highlight a few key areas and show some of the key research ideas in that space. So today's lecture is primarily for your own kind of background on this topic. Okay, and I'm going to be using some of the slides from Emilio's talk. Okay, so throughout this class, we've looked at supervised learning models, right? We've looked at unsupervised, supervised. We've seen convolutional networks. We've seen variational autoencoders. We've seen GANs, and a whole bunch of different models. But again, most problems that you can think of, most successful problems so far, you can think of them as mapping inputs to an output, right? You have an input, you're mapping it to an output. Think of it as machine translation, or classification, regression, or pretty much most of the things that we've covered in this class. And the environment is typically assumed to be static, right? It doesn't change over time. Typically, outputs are assumed also to be independent of another. So for example, labeling one image doesn't affect the next one, right? So if I show you an image of a cat and then I show you an image of a dog, one doesn't really influence the other one. But typically, when you look at the environments are typically dynamic, and they can change over time. And so if you think about building an autonomous agent, you have to be able, the agent has to be able to handle new environments. Actions that you take can affect an environment with a very long time lags, right? So buying a stock today, years in the future, you may lose all the money. Right, so that action may have an impact very far into the future. Labels can also be very expensive or difficult to get. So for example, if you're trying to get your swimming octopus robot to swim, it's very difficult to specify precisely the optimal actuations of the swimming octopus, right? So generally, getting very precise labels is a difficult task. So reinforcement learning relies on a very simple sort of idea. And again, that in itself, the reinforcement learning in itself is, I think there's going to be a class in the spring on reinforcement learning, deep reinforcement learning. So you can teach the entire class on that subject, right? So I'm only giving you a very short highlight of what's going on. But in the reinforcement learning paradigm, you have an agent. The agent takes an action. Think of an action as, maybe a set of discrete actions that you take. It could be continuous action, but typically it could be discrete. So you take an action, you have the environment. The environment provides you a new state or a new observation, right? Depending on your actions. So your actions actually can impact the environment. The environment gives you the new observation. And once in a while, you get the reward from the environment, right? So you can think of it as instead of giving you a label, you get the reward. And high reward basically means good behavior, right? So you always want to take actions that have high reward. Rewards typically are very sparse, so you don't get the reward at every single time step. Think of the system as that you take an action, you get the observation. You take an action, you get an observation, and after some time, you get some reward saying this was a good behavior, or this was a bad behavior, right? Reinforcement learning, you can think of reinforcement learning as the way of learning policies, right? What you want to do is you want to map observations to actions. And think of an observation as some high-dimensional observation. That could be an image, or could be a speech, or a sound, or anything that you can think of what you're observing. And you want to map observations to actions, much like what we've seen in supervised learning, right? I give you an image, I want to label it. Or I give you a text, I want to translate it, right? Pretty much the same idea. You get an observation, you take an action. It's just that in reinforcement learning, the key difference is that in reinforcement learning, nobody's telling you whether the action you're taking, immediate action you're taking, is good or bad. So think of it as kind of a system where you're trying to label the image, but nobody's telling you, are you labeling correctly or not, effectively, right? Through the sequence of actions, once in a while, you get the reward saying this was good, this was bad. And your goal is to maximize the long-term reward. And these kinds of systems allow you to learn some behaviors, some meaningful behaviors in dynamic environments. Now, deep reinforcement learning is something that's been gaining popularity in the last few years. And the way you can think about deep reinforcement learning is just a way of parameterizing the policy, right? So you have an input, which could be an observation, could be high-dimensional observation. You pass it through a convolutional network or a deep network or recurrent network or whatever your favorite architecture is, some high-capacity representation model. You take an action, okay? So the output of the network is actually the action that you want to take. And you're adapting parameters of this model, of this network, there's a whole bunch of different algorithms. There's something that's called Q-learning. There's something that's called actor-critic. There's versions of asynchronous, advantage-active critic algorithms. There's been recent work on evolution strategies, which you can think of as a finite difference method for adapting the parameters, right? So let me show you an example of learning to play a three-dimensional game. So this is learning to play a three-dimensional environment. So let me just explain what this is. Let me stop here. So what you see here, it's a little bit dark. This is a Doom engine. So what you're seeing here is the input to the algorithm is just a frame, right? What you're seeing. The output is a set of actions: turn left, turn right, move forward, go sideways, and in this particular case, the reward comes from collecting objects. Okay, so think of it this way: you have a system, you have some input, pixels, you can take actions. And your goal is to learn to navigate in this 3D dimensional environment so you don't get stuck. And the only thing that you get from the environment in terms of reward is collecting objects. So you're basically telling the system, do whatever you need to do whatever the actions you need to take in such a way that you collect as many objects as possible, right? And obviously, if you step in lava or if you step in some areas, you basically die and you get negative reward, right? So avoid the obstacles and move in this environment. And this is what the system learns to do. So after 5 minutes of training, it's kind of, it moves around and then it gets stuck in the corner. Can't get out of the corner. Because to get out of the corner, you have to take a sequence of left action. After a while, it actually learns to navigate in this environment, right? So now it gets stuck because it doesn't really see this barrel here. So now, and it's interesting because you're not really telling the system what you need to do. You're just telling the system collect as many objects as possible, and it learns to navigate on its own, right? And it just learns to avoid lava and those things. You can now learn to train, to navigate in these actions, in these different textures. And then the interesting thing is that once you put the agent into the new environment, completely unknown map, the model has no problem navigating in this unknown environment, right? So this is the map that the model was never trained on, right? It's the first time it sees this map, and it has no problem basically moving in this three-dimensional environment. Okay, now, so this was, and there's been a lot of recent work, people learning how to walk and so forth, right? So these are not simple kind of behaviors, but the model is able to learn them. Now, what I'd like to do in this particular talk, the last talk, is show you one area of research which is called learning with memories. One of the things that you've seen in the previous example, when the agent moves around, the only thing that it remembers is that here's the input, you take an action, and then depending what action you take, turn left and right, you have another input, you have another action, but the model completely forgets what just happened in the past few frames, right? So you can think of it as a reactive agent. Given the input, you take the action. Given the next input, you take another action. There is no notion of remembering what happened in the past. And this is one of the key problems in terms of how can you learn some external memory? How can you memorize something that you've seen in the environment so that you can act optimally in the future? So think about agents that can build strategies, that can learn something about the environment on their own. And then in this case, there is a need for these memory mechanisms. In the last couple of years, there's been very nice work coming out of Alex Graves. And you can think of them as an agent with a more advanced external memory. So you have a mechanism where you can learn what to write into the memory, and you can learn what to read from the memory. And I'm going to show you some examples of that. But these memory systems are very difficult to train, especially using reinforcement learning. Okay? So there has to be a way around it. Now, why is memory challenging? Well, here's an example of why it can be challenging. Suppose you have an agent in a simple random maze, right? The agent starts at the top of the map, and the agent has shown an indicator near its initial state. Okay? Now, the color of the indicator determines what's the correct goal. Okay? So if it's green color, then the agent has to find the right target. If it's a pink color, it has to find the cyan state. Okay? Now, if you look at these settings, if I told you what the rules are of the game, if I told you, if you see this, find this target, if you see this other thing, find another target, then the problem is very easy to solve, right? But in this setting, if we don't give any information to the agent, how can the agent learn that there is something in the environment called the indicator that really is telling me which target I should be going, right? Intuitively, what happens during the learning process is the agent starts, it moves around randomly in the maze. It's a random maze. You've never seen this environment before. You move around up until you hit maybe the red target. Let's say you hit the red target and get positive reward. The learning algorithm will say, aha, whatever sequence of actions I've taken, because I got positive reward, try to do that sequence of actions again, right? Let's say at the next episode, you move around, and then you hit again the red target, and you get negative reward, right? So now the agent has to figure out, okay, sometimes I get positive reward, sometimes I get negative reward. Why is that? And through the learning process, it can eventually figure out there is something in the environment that's called the indicator, and depending on the state of the indicator, that tells me what's the right state I should be going to, right? So it's very easy for people to solve, but it's very difficult for machines to solve. And in particular, the distance traveled between the indicator and the target could be very large, right? So traditional models like recurrent networks, LSTMs, and such, they can't really solve this problem. LSTMs and RNNs, they can maintain information for maybe, tens of steps. After that, it's very difficult to propagate this information, right? So you have to have some form of external mechanisms where you're actually explicitly writing something and storing in the memory, right? So it's almost like discovering these kinds of rules that you see in the environment. Yes?
So if you use like other triviality traces, it's the same problem if you have the recurrent network?
Yes. You do have the same problem because ultimately the distance, for example, if you make these mazes larger, the distance from when you see the indicator and by the time you actually find what the target is could be very large, right? So here's, at the start, you don't have any prior knowledge to store the color in the memory. If somebody told you that you need to store this color, then things would be easy. right? Because you could just store it and then move around and just retrieve it. The issue is that, how do you learn what to store? Because there are a bunch of other objects could be in the environment, right? How do you know which one associates with a target that you need to go to? So the following must hold. You have to write the color to the memory at the start of the maze. You never overwrite memory of the color for t time steps, so you have to maintain it. And you have to find and get to the right goal, right? So one solution is basically write everything into memory. And this is something that's, in the last few years, there's been a body of work on memory networks. And the key idea of memory networks is you basically storing key and value for m lost frames. And m can be very large. Think of this as basically saying, what I'm going to do is I'm going to store everything that I'm seeing, right? So you store everything that you're seeing, and then the reading operation, when you're trying to read, you basically have a softmax probability. It's like attention. So the reading operation is attention over what you've seen so far. So you build an attention over what you've seen so far, you pick up the right part, and then you use it as an input to your policy, right? So in principle, this works reasonably well, right? But obviously, it's easy to learn, right? You're actually not learning what to store. You're storing everything. But it can be inefficient, right? So you need m to be bigger than the time horizon of the task. So your m has to be sufficiently large so that you don't forget what you've seen when you've seen your indicator. You might store a lot of useless redundant data, right? Because if you're moving around and you come around to the same location in the maze, you kind of seen this location, you're just going to be remembering everything. And the time-space requirements also increases with m, right? What is it that you need to store? So it's almost like, I remember there were a company that was trying to build cameras such a way that if you wear the camera, it can record your entire life, right? So you can, in principle, record everything that happened to you in your entire life's time span. And you can use, in principle, this attention mechanism to kind of read the relevant pieces, like where have I left my car keys? And, it will find it for you, right? Or what happened when I was 6 on my birthday? It can remember. So it's just a retrieval problem, right? If you store everything, it becomes a retrieval problem. But again, all these concerns, all these things basically remain, right? So the big question is, can you actually learn what is it you need to store, and can you learn how to retrieve the right information? So here's the idea of a neural map, which is we're going to be using writable memory with a specific inductive bias. Okay, we're going to structure memory into W by W grid of k-dimensional cells. Now imagine that we're navigating in some unknown environment. Think of it as a map of the environment. It's a 2D environment. We're going to be storing everything, structure memory in WW grid of k-dimensional cells. And then for every xy position, we're going to be writing into x prime, y prime in a W by W grid. Okay, so the idea is the following. I'm going to write what I'm seeing at this location. When I move to this location, I'm going to write it here. When I'm at this location, I'm going to write it here, right? So you can think of it as my map is a 2D representation of where I am in the environment, right? So it kind of explores a little bit of a topological structure. There is one thing that I'm using here, which is I need to know the map, and I need to know the location of where I am on the map, right? So these sometimes can be unrealistic assumptions, because sometimes if your GPS is not quite working properly, you don't know exactly where you are on the map. And so then there are approaches such as localization. You have to localize where you are. And then if you want to go beyond that, there's something called simultaneous localization mapping, so you can build the map of the environment. But let's just make an assumption that we will know where we are, and we also know the map. All we're trying to do right now is just basically figure out what is it that we need to write in the memory, and how do we read it from the memory, right? So neural map acts basically as a map that the agent fills out as it's exploring the environment. And we have an inductive bias, which is a sparse right. And this inductive bias prevents the agent from overwriting the memory too often. So we can actually learn when we need to write. If we've already written this part of the memory, maybe we don't need to overwrite it. And so how does it work? Well, it works as follows. Here's your state, which is, again, think of it as a three-dimensional environment that you're seeing. You create features out of it. Think of it as a writable vector. What is it that you store? Think of them as convolutional features that you get out of your environment. And then you write them into the memory, because you know your location, so you write at a specific location, and then you take an action. Action could be turn left, turn right, move forward, right? At the next time step, depending on the action, your environment gives you the next observation. You read from the memory using attention, which is essentially tells you which part of the memory I need to read. Then you update your memory with the new information, and then you take an action, right? And so forth. So at the nutshell, you can think of this memory block as like a very specific three-dimensional structure that evolves over time. So it's almost like introducing some structure into the states of recurrent network. Because you can think of this entire process, this memory evolution, as a recurrent network, but with a very specific inductive bias, right? And we can write and we can read. So we're learning what is it that needs to go into the memory, and we're learning what is it that we need to be reading from the memory. We're not really specifying a priori what needs to be written and what's need to be, and how we read it, right? So the entire process here is differentiable. I'm going to show you what the set of these equations are that allows us to build a fully differentiable model with the memory. Okay, so in terms of the operations, we have two read operations. There's something that's called global summarization, and then there's something that's called context-based retrieval. Okay, then we have sparse write operation, where we're writing what we're seeing into the memory, and then both read and write vectors are used to compute the policy. Okay, and the policy is basically taking an action. Think of the policy as just softmax of possible actions to take. It's almost like solving classification problem. Which action do I need to take, given all the information that I have so far? So read operation, you're basically reading from the entire map using a deep convolutional network. And you can think of it as a vector that provides a global summary. Now notice when you start at the very beginning, most of the summary here, most of the input is going to be 0, because we haven't seen this part of the environment. It's going to be zeros, right? But you can think of this, again, global read operation is just summarizing what you've seen so far. Now let's look at the context reading operation. Context reading operation is just basically attention. Okay, attention that that we've seen in our class, right? When we looked at machine translation systems and RNNs. So this is just a basic attention mechanism. Let me show you what it does intuitively. So imagine that I give you the state, right, image, or some features of the convolutional model. I give you the global context vector, which is, you can think of a summary what's in the memory so far. And that, if you concatenate both of them, that produces a query. So think of the query as, the vector that I'm getting so far. And let's say I have 2x2 memory block, right? Just for visualization. So what I'm going to do is I'm going to look at the dot product between query vector, Q, and every memory cell, right? So I'm looking at the dot product, and I pass this dot product through the softmax, right? If I pass it through the softmax, I'm going to get these similarity scores alphas that sum to 1, right? Now what I'm going to do is I'm going to do element-wise product between the queried similarities and the memory cells. I sum over all positions to obtain a context read vector C sub t. Okay, so what it is doing? This is essentially saying, find me the location in the memory that's closest to my query vector, right? So it's basically saying, find me which one of these blocks in the memory is closest to my query. And that's exactly what attention does, right? Think of it as retrieval You could do retrieval. You could say, find me the closest one over here in my memory and just retrieve that block. What I'm doing is I'm doing soft way of retrieval. And the reason why I need to do it in a soft way is because this entire operation here is differentiable. So I can backpropagate through the whole system, right? And this is exactly what the soft attention does. So what the reading operation essentially is doing is basically saying, well, I'm looking in this environment. And if I want to retrieve something from my memory, I need to basically find some similarity between what I'm seeing so far and the memory, right? And what's written in my memory. So I need to kind of learn that essentially what the model is learning is that when it finds the target, like a red target, it's learning to associate red target with a pink indicator, right? And it learns that these two colors should be similar, essentially, right? And so now it can retrieve the right information from the memory so that it can find the right target. So this is nothing more than just an attention mechanism. Okay? Any questions? Now, the writing operation is very simple. You're basically creating a new k-dimensional vector to write to the current position in the map. And then you're saying, well, update the neural map at the current position with the new vector, right? So this is WT plus 1. That's what you're seeing. And then you're basically updating it. You can also use gating, which is a way to say, well, instead of updating it, I'm going to have a gating mechanism that tells me how much of a writing do I need to do. If the value of the gate is 1, you're basically using completely overwriting your memory. If the value of the gating is 0, you're basically not writing into the memory, right? So it's very similar to what we've seen, for example, in our last lecture, where we're choosing between characters and words, right? And we use the sigmoid function based on some hidden states to say, should I be using characters or should I be using words? And then do the soft weighted average over the two. That's exactly what's happening here between these two states. Yes?
You're only updating the correct, like the exact position, right? Of them.
Yeah, that's right.
Like, why don't you do it like in an attention way too? Like, if you say you have noise and you don't know exactly where you are.
Yeah, you can extend it. You can extend it to say if you have some noise in your exact location, you can write softly around your area. Yeah. This done. I mean, there's been some. For example, if you look at the neural Turing machines, what they're effectively doing, the writing operation, is they're doing attention of the entire memory and like doing sparse write over the entire memory. But generally, this becomes very difficult because ultimately you want to write at one location because that's your data. It's kind of difficult to say I'm going to write a little bit at every single location. At the next time stamp, I'm going to write a little bit in every other location. So just learning these models becomes way more difficult. So the inductive bias here is that you're only writing at one particular position. Yeah, but you can extend and deal with noise and extend it to writing a little bit around you as well. And now you're basically using these features, the global read, the context read, as well as what is it that you're observing, your features, and into producing some policy of the actions by passing them through some perception or some a simple neural network. So here's what you can do with this system. This is a real map. This is not visible. And this is what the agent sees, right? It's a partially observed environment. So the agent is seeing, this particular observation. So this is the only thing that the agent sees, right? And again, if you add a little bit of noise, the results turn out to be, fairly robust. It's not like you need to have a precise. Like if you mess up a little bit in terms of where you're writing, it's okay, as long as at some point you're not completely lost where you are in the environment. Because if you're lost where you are in the environment in this maze, then you're just going to be writing in the wrong parts of the map. So here is a system that basically learns. Let me just pause it to tell you what this is. So here is a system where, in this particular setting, you get the pink indicator, and in this case, you actually have to go to the green target. If you've seen, I guess it was a yellow indicator, you have to go to the red target. Okay? So this is an environment where this is a random maze. So this is the maze that the model has never seen before. It's never trained on this particular environment. So obviously it's a random environment. It has to move around to find the targets, right? We don't use, we don't give the information about the map to the agent, right? So the agent has to explore. So now if you're seeing this particular indicator, you have to find this target, okay? So what the model does, let me just replay it. So what the model does, it moves around, it finds the wrong target, it backtracks, and starts exploring the environment up until it finds the right target, right? And you can see that the distance, when it sees the indicator, and when it has to make a decision of, going to the right target, is, can be quite large. And now it finds the right target. What happens in this particular setting is that when it was here, it looks at the wrong target. If you look at the attention, the reading operation is actually reading from the memory where the indicator is. So it's learning to read from the memory for the location of the indicator, because if it can read correctly the state of the indicator, it basically learns that this is the wrong target to go to. Because if you go to this target, you get negative reward, right? So this is, again, a very simple, but turns out to be extremely hard, right? And in general, you can make it arbitrarily hard even for humans, right? Because there could be a lot of things that are happening in the environment, and maybe the speckle that you see over there will determine which door you have to exit from, right? Like, that would be a hard problem for you to solve. Do you know what I mean? Like, if I have, like, let's say there are 2 doors or 3 doors to exit, and I tell you, figure out which door to exit, and then, whether I have iPhone 10 or iPhone 7 determines which door you should exit from, right? That would be a very difficult task for you to solve, in principle, right? If I didn't tell you anything about the environment. Because anything could determine what your actions should be. So you can make this task be arbitrarily hard. These are just some examples of a system. So one thing that I want to highlight is one example that I want to highlight is that LSTMs, let me see where the LSTMs are. So LSTMs, you can see that they reach some performance, but then they can't go beyond that. And what happens with LSTMs is basically for short mazes, or if your indicator is very close to the goal, because this is my indicator and my goal is over there, then it's very easy for me to solve this problem because I immediately see where I need to go, right? And this is exactly what happens with LSTMs about 20% of the time, because these are randomly generated, and the placement of targets and indicator also randomly generated. So if they are close to each other, LSTMs can solve it, because you don't really need to store for a long time. You can just basically use LSTMs, and with a few time steps, you can propagate the signal forward. Memory networks do reasonably well, but then again, this is an environment where you're always constrained by how much you need to store. So if you store the entire history, which I think was happening here, you store everything that you've seen so far, it does reasonably well, but you can see it doesn't do as well as LSTMs, and particularly neural net with gated recurrent units. So this is interesting. And if you just do random, I guess random is just kind of like just take random actions. So basically, random action is about 0, right? This is in terms of return. I guess this is in terms of the reward. So random actions are about 0, which makes sense, right? Because half of the time you bump into red state, half of the time you bump into green state. So on average, your expectation of your reward is going to be 0, right? Because half of the time you'll hit it correctly, half the time you'll hit it incorrectly. So on average, it averages out. You can also do it in terms of the 3D environment, in a Doom environment. So this is again. So the previous one was on kind of random mazes. These are 2D mazes. This is if you actually do it in a 3D space. So these are results are a little bit older results. The new results are a little bit better. But then again, you can see that in some cases, these models do quite well, right? You can also add an LSTM layer to the neural map that improves things a little bit, so you can have some short-term information as well as storing long-term information into the memory itself. Now, in terms of how can you improve these systems? Well, as I mentioned before, the big problem with neural map is that it requires mapping from x, y position to x prime, y prime position on the map, right? Essentially, it requires you to know exactly where you are in the environment. So we need to have already solved localization problem, okay? There is some work on active neural localization that allows you to localize in the environment given some landmarks. So you can, in principle, solve this problem so you know exactly where you are. Or you can go around a little bit and say, well, you're going to obtain a map which is egocentric. So the agent always writes to the center of the map. And when the agent moves, the entire map moves by the opposite amount, right? So you can think of it as you're always writing in the center of the map. And depending what action you take, the map moves around in the opposite direction, right? So this is sort of like a local, a little bit of a local model. So it doesn't really require you to know exactly where you are on the map to solve this task. Now, I think that we've talked about this before. Memory is not just used in reinforcement learning. It's also used in language. Right? So last class we've looked at the example where how can we take some structure, some information like coreferences, entity relations, and such to embed into the recurrent network so that we can have better text representation, right? And we've seen this example in the last class where we can augment. So if I give you a sentence, Mary got the football, she went to the kitchen, she left the ball there. We can connect Mary, she, and she. It's a coreference. Basically meaning that these things mean the same thing, as well as ball and football. These are synonyms. They also mean, the same thing. So what you can do is you can create this acyclic graph encoding scheme, which is memory as a acyclic encoding graph, which is essentially telling you what connections should exist. So you can store previous states, previous hidden states in your memory, and then when you're taking, when you're getting to the next hidden state, you can use the memory from the previous hidden states as well as what you're seeing into the RNN. So you can basically use the memory and come up with just a representation of a recurrent network. So here again, just wanted to highlight that memory is not just used in reinforcement learning, but it can also be used in language, right? And we've seen some examples of that as well, like memory networks, for example. But here's what you can do if you I don't think I've shown you this example. This is what you can do if you incorporate these core references and incorporate the memory. So suppose I give you these 4 sentences on the right? Sandra went to the hallway, Sandra grabbed the apple there, Daniel moved to the kitchen, Sandra got the milk there. Okay? And I give you how many objects is Sandra carrying? That's the question. And what I'm going to do is after every single sentence, I'm going to try to answer that question. And you can use your standard kind of reading comprehension models, the ones that we've talked about yesterday. In this case, it's a GA reader, gated attention reader. So what's interesting here is that after the first sentence, Sandra went to the hallway. If you're just asking the system how many objects is Sandra carrying, the model would produce 1. Okay? And then if I give you 2 sentences, Sandra went to the hallway, Sandra grabbed the apple there, and I say, how many objects is Sandra carrying? You'd also say 1, right? And so why is that? The reason why, the model's basically pretty much ignoring the input. And if somebody is asking you how many objects someone is carrying, the answer 1 is a pretty good one, because most people carry only 1 object. So you can hit like 90% accuracy just by answering always 1, right? Which makes sense. But if you're actually using this attention mechanism and you're using the memory, then the model does something more reasonable, right? Like if you say Sandra went to the hallway, how many objects is Sandra carrying? You say none. And then you go to 1. And then after the third sentence, Daniel moved to the kitchen. The model is confused a little bit. It thinks 1, but it could be 2. So it's not perfect. But after the last sentence, the model quickly sets 2 objects, right? Cassandra grabbed the apple and then she grabbed the milk. So the answer is 2, right? So you can see that just basically having a little bit of memory, so you know that Sandra means, and Sandra, all Sandras here, they mean the same thing, right? Because they're connected through these additional links in a recurrent network. So that definitely is helping by a substantial margin. And ultimately, what a lot of people are doing is, if you want to build intelligent agents, you want to be able to learn external memories. You want to remember what happened in the past. So as to learn what actions you should take, what optimal actions you should take in the future. So that area of research, learning the memory, is actually very interesting and has a lot of potential. And this is different from a lot of existing algorithms, right? If you think about convolutional neural networks, if you think about recurrent neural networks, all these models basically learn, or maybe the information is sort of contained in the weights of the model, right? Think of a convolutional network that classifies images of dogs. All the information is in the weights of the model. There is no memory component. There is no storing. There is no explicit mechanism to store information. Whereas these learned external memory mechanisms is a little step forward in terms of designing architectures, specific architectures where you can learn what to store and you can learn how to read, right? So you can eventually learn the useful information to store for your task and how to retrieve that information from the memory, right? These are not discrete operations, just read and write. These are actually differentiable operations. It's kind of like differentiable read and write operations, which is kind of interesting. And also, how can you reason and communicate with the agent, right? So we've seen some examples of reading comprehension on that. Here is another example of, let me just pause it and show you what this is. This is a system where you're basically telling the model, go to the red short torch, right? And this is poses the reinforcement learning problem, which is to say, if you find the red short torch, you get positive reward. If you don't find it, you get negative reward. So the question is, can the model learn what does it mean to go to the red short torch, right? It has to learn something about colors. It has to learn something about what does it mean short. Like if there are 2 torches, one of them is shorter than the other one, it has to learn to figure out the height of one torch is smaller, that means short, right? Because sometimes it's very difficult to explain like precisely what does it mean short. And so this is the system basically learning to do that. And you can see after 30 minutes of training, it's completely confused. The other thing is that it has to move around to find out what the object it has to go to. So it has to learn what is a short torch. It has to learn was a tall red pillar or green torch. It has to learn the meaning of the word like smallest objects or tallest object and tallest red object, right? So after basically a lot of training, 72 hours of training, it's basically learning to do a little bit of reasoning. It moves around, it finds the right target, like smallest green object. Like what does it mean smallest? Right, so it has to you're not telling the system the meaning of the smallest is you have to estimate the height and then if this height is less than this height, then it's smaller than this, right? So it's just kind of learning on its own what does that mean, and so after a while it's basically now again this is a very constrained environment. Obviously, there are only I believe on the order of 70 instructions that you can do. But the model does learn something like, it learns, if you look at the representation of the word blue, it maps colors into the same semantic space, right? It maps torch and keys and such into the other semantic space. It can generalize to new instructions, like it's never seen smallest torch at the training time, but it's able to generalize at the test time. If I tell the system, go to the smallest torch, it learns what does that mean. but it's seen smallest keys, it's seen smallest scullies, and seen like other combinations, but not that particular combination, right? So this is a setting where it's actually learning to generalize, and the model is actually pretty simple. It's also based on attention, gating attention mechanism. So this is a setting where you have the natural language instruction. Oh, by the way, I should also point out that it can do things like if I'm in the environment and I say, go to the tallest object, it goes to the tallest object. If I take the same environment and remove the tallest object and again tell the system, go to the tallest object, it finds the next tallest object, right? So it's sort of learning a little bit to reason about the meaning of the word tallest, for example. So it's not just the color or the object itself, it's some kind of comparative thing that it's actually learning. You have an image, it goes through the convolutional network. There is something called multimodal fusion, which is a gating mechanisms where you combine features that are coming from instructions and features that are coming from the image. And then that goes into the policy learning module, which produces the policy. The policy is, what action you need to take so that you can reach the correct target. Okay? And obviously, there's a lot of work that can be done here. There's a lot of work that can be done using attention, maybe better attention mechanisms, so the model can focus precisely on the green or the torch. Right now, it really doesn't do that, so it just aggregates that information. So there's definitely more sort of more ways to improve the model. Okay, so the final piece, one of the areas where there's a lot of research happening is can you extend these models to the multi-agent domains? So instead of having a single agent, can you learn multiple agents? So multiple agents communicated perhaps through a shared memory. Right, so this is an area of research which is picking up a little bit. How do you design communication protocols? And how do you actually learn what to communicate? Like how can you evolve your own language, your own communication language, so that you can achieve a particular task that you're trying to achieve? So I think that Emilius tried looking at the multiple agents, and we sort of find suboptimal behavior. If you put two agents in the environment, what should happen is that both agents should be exploring the environment. That would be the optimal behavior, writing everything into the memory, up until you see the indicator. Once you see the indicator, you can write into the memory, and so that both agents would continue exploring up until one of them will find the right target, right? Like the right door, for example, to exit. But what the system does is it basically, once one agent finds the indicator, the agent basically stays there and just communicates the hidden state of the observable to the other agent. And while the other agent moves around and tries to find the right target. So it's sort of learning to ignore the memory, and just one agent is acting like a memory, just standing, just looking at the indicator every single time step and communicating the state of this indicator to the other agent, instead of writing into the memory and continuing to explore. So it's interesting. That basically means that optimization is not quite there yet. It does something reasonable, it solves the task, but not optimally. So another area is that can you train an agent that can learn to simultaneously localize and map its environment using the neural map, solve the problem of needing an oracle to supply your exact position. So there is some work, and this is a pretty big area of research. I mean, if you are in the robotics community, you probably know, if you just Google SLAM, simultaneous localization mapping, there's tons of papers written in that domain. But a lot of existing algorithms, it's very difficult to deal with environments where it's very dynamic, things are moving, you have different lighting conditions, particularly if you're trying to look at high dimensional inputs like cameras, for example. So this area of research is actually pretty interesting. So there's a lot of things that can be done. And also, can you structure neural maps into multi-scale hierarchies? So there's a whole area of research of building hierarchical reinforcement learning algorithms. Or in this case, can you build a multi-scale hierarchy so that you don't write into every single location, but maybe you have a multi-scale resolution of your environment, right? So you roughly know where you are, and maybe you don't need to write every single detail. You only need to write the important information. So you can build, the multi-scale representation of that. So there's still some room for improvement. So on that note, I think I'm done. If you have any questions, let me know. We still have a little bit of time, but and then again, if you're interested in reinforcement learning class in the spring, the reinforcement learning class will deep reinforcement learning class will effectively dive into specific learning algorithms, and then we go into more details about how do we define Markov decision processes and combining deep learning and policy approximations to solve these kinds of tasks. And we're going to dive a little bit deeper into reinforcement learning with memory and a whole bunch of different algorithms. Any questions? Yes.
So for this is this map where the memory is only picked up after 20 epochs or something. This is all simulation. I don't know how many runs you had, 1 million maybe or 2 million runs. What if I have a real system, I have 200 runs maybe? All these memory methods, will you ever think they will be feasible, or is it?
Yeah, it's a very good question. So the question really is, you can run these things in a simulator, and as you've seen, for example, in a language grounding task, it takes many hours and many, I think on the order of thousands of simulations. The nice thing about working in a simulated environment is that you can parallelize, and you can run at time which is much faster than real time. So you can really afford, running in the simulation for, billions of runs, exploring the environment. How do you transfer it to the real world? If you have a real robot, you can't really do it with a real robot, right? With a real robot, you can only maybe do 5 runs or 10 runs. You can't really do billions of runs. So there's still an open question. How do you take these models, trained in the virtual environments, and translate them into the real robot? That still is an open question. And there's still some debate about it, which is some roboticists believe that if you just build in the simulation, you can't translate it into the real world. But at the same time, you need to be able to, leverage the simulation, because sometimes it's very difficult to even test your robot in think about, you're trying to pilot the drone, right? And you want to be able to learn to do some kind of emergency maneuvers when the drone is about to hit the tree, right? You can't really afford, with a real drone, crush the drone into the tree 1,000 times to learn what maneuvers you should be taking, right? That just doesn't make any sense. You can do it in the simulator, but you can do it in the real world. Or your drone moves around and hits a human, right? How do you avoid that? You can't do it in real life. So this area of research of going from simulation to the real world is still an open area of research. Nobody knows. I think that the question really is going to be, can you use some kind of domain adaptation techniques? Can you abstract something from the simulated environment in the real environment so you can do some domain matching between the two? But there's been some papers basically showing that if you train a robot in a simulated environment to move some blocks, and then you take the exact same algorithm and put it into the robot learns to move blocks in the real world, achieve the task of putting blocks in the right places in the real world. So there's still some hope that training in a simulation, maybe in some virtual environment, transferring into the real world might work. But ultimately, in the future, there's just going to be more and more algorithms. The nice thing about the simulated environments and in machine learning, you see a lot of people working in that space because we don't really nobody wants to deal with real robots. Real robots, they break down, you have to fix them, it's they run slowly. In simulation, you can just parallelize across 50 GPUs and get interesting results, but the question still remains, how do you take that and put it into the real, from the virtual environment, put it into the real environment? So that's open area of research right now. Yes?
When you parallelize, how do you communicate the learning information from?
Oh, you just buy a really good machine with a very sort of nice communication protocol. because you can parallelize across multiple GPUs. There are also sort of algorithms, sometimes called asynchronous methods, that don't require you to, one model can learn, the other model can learn, and they can just communicate to the master model asynchronously. So there are ways to scale it up substantially. It's a combination of GPUs and CPUs, but a lot of people are working on that problem. So you can really scale, you can really run, hundreds of simulations at the same time, exploring the environment and then learning what the policy should be across multiple GPUs, across thousands of CPUs and such. But again, the question still remains, you can't really do it on the real environment. And ultimately, showing you results in a simulated world is good, but ultimately it will have to work in the real world. And that still is an open question. Other questions? All right, good. So let's finish here. So continue working on the projects. I think you should have gotten some midway reports back. So take those reports into account from your TAs. I think most of the TAs are away this week. There's